This is an introduction to the chi-squared test for independence based on a contingency table or two-way table. And it is a hypothesis test very similar to all of the ones we've done. They all have the same backbone, the same structure. And it starts off with somebody making a claim about a population. So Olivier claims that girls are more likely to prefer pink than boys, sort of thing that he'd say. And what he's doing is saying that there is a population, an infinitely large number of people, and that each person has two variables. One of them is gender, and the other one is what color they prefer. Let's say pink against blue to keep it simple. And Olivier is claiming that those two variables are linked in some way. So, like all hypothesis tests, we start off with a null and alternative hypothesis, and the null hypothesis is the neutral ground. What is the neutral position on this? And it is this: gender is independent of colour choice. What Olivier claims is saying that it is not independent. They're dependent in some way. There's some relationship or link between them. So the neutral position is no, there's no link at all. You are going to have to provide evidence for us to reject this null hypothesis. That's the same setup as every hypothesis test. So we go and ask 100 people whether they like pink or blue. And let's have a look at the data. First of all, notice that in the real world, we're never going to be able to get exactly the same number of boys and girls in our survey. And anyway, that might not be the right thing to do. In our population, there might be more girls than boys. So this is what we have done. We've got 60 girls and 40 boys. And notice that blue is more popular, regardless of gender. 80 out of the 100 people prefer blue. So the question is this enough data to back up Olivier's claim? Does this tell us that boys prefer blue more than girls do? Well, what we have to do is consider what would we expect to happen. So if the null hypothesis is true, and this is such an important concept in all hypothesis testing, let's assume the null hypothesis is true. What would we expect to happen? And then we can judge whether we should reject it or not. So imagine the null hypothesis is true, that gender has got nothing to do with your choice of pink or blue. What number would you expect to go in this box? How many boys would you expect to choose pink? Think about it. How would you work out that number? Now, what you can't do is say, well, there's 40 boys. We'll put 20 pink, 20 blue. It's even. We can't do that because we know blue's more popular overall anyway. How can we reflect the fact there are fewer boys than girls and blue is more popular than pink to pick a number out here? And the way we do it is this. We say that we know that 20 out of 100 people, 20% of people prefer pink. Now, because boy and girl gender has got nothing to do with that, I would expect 20% of boys to prefer pink, and I would expect 20% of girls to prefer pink. So 20% of the 40 boys should prefer pink. 20% of 40 is 8. I would expect 8 boys to prefer pink, and therefore 32 boys to prefer blue. Now 20% of the girls, I would also expect them to prefer pink. So I would expect, that's 12. I would expect 12 girls to prefer pink, and therefore 48 prefer blue. So I'm basing this on the assumption that the null hypothesis is correct. And so what I have here is two tables. I have one table of what actually happened, and one table of what I would expect to happen if the null hypothesis is correct. And the idea of a chi-squared test is, I'm going to say, if this data is sufficiently different from this data, then that means that there's something wrong with the expected table. The observed data is so different to the expected table that we say, well, the expectations must be wrong. And the expectations are based on the null hypothesis. So if the observed data is a long way from expected, we can reject the null hypothesis. So how do we measure the difference between these two tables? Well, what we could simply do is take the observed number, 4, and subtract the expected number, minus 4, and do that for all 4 positions. So that is observed 1, 2, 3, and 4, and expected 1, 2, 3, and 4. And we could add that up, and that is a measure of the difference between these two tables. The problem with that is that some of them are negative and some of them are positive. It'll cancel out. So to avoid the cancelling out problem, we square it. That's where the chi-squared comes from. We square it. So now we say, well, the difference between 4 and 8 is 4. Square that, 16. The difference between 16 and 12 is 4. Square that, also 16. Add that up. And we add up the 4 of these numbers, 4 of these, and we end up with a chi-squared value. So that chi there, this is the Greek letter chi. The chi-squared value is this. Now the problem with this is that what happens if we had 4,000 boys and 6,000 girls to choose from? The chi-squared number would be much bigger, and therefore we couldn't use it to compare. And so what we do is we do this. We divide by the expected value, and what that does is it standardizes everything, and it means that we can compare two-way tables of any size, of any number of people, and we always get a chi-squared number that is comparable. Now, what chi-squared doing then is it's measuring the difference between what happened in reality in the observed world to what happened when we calculated things based on the null hypothesis. And if the chi-squared value is high, we're going to reject the null hypothesis. And if the chi-squared value is low, then it's saying that the two tables are quite similar, and therefore there's not enough evidence to suggest that these are different. We would accept the null hypothesis. Now, this is all done entirely on the calculator, and that was just for your general understanding.